What's going on, guys? Let's go over section 5.3, diagonalization, okay? So here's section 5.3, and the very first thing is the first two sentences in the first paragraph, so let me read them. In many cases, the eigenvector information contained within a matrix A can be displayed in a useful factorization of the form A equals P D times P inverse, where D is a diagonal matrix. In this section, the factorization enables us to compute A to the k quickly for large values of k, a fundamental idea in several applications of linear algebra. Okay, so let's move on to example 1. Here is D. Now to compute D squared, you multiply D with another D. And the thing is, because of the arrangement of the 0 entries in the matrix to the non-zero entries, D squared really becomes 5 squared, 0, 0, 3 squared, okay? Nothing changes except that the non-zero entries are raised to the corresponding power. Same thing with D to the third. Look, the non-zero entries are raised to the corresponding power, and the 0 entries are just left where they are, okay? And this pattern is applied to a general matrix D to the k. The next important thing is this sentence right here. If A equals P times D times P inverse for some invertible matrix P and diagonal D, then A to the k is also easy to compute. And we already saw this, right? So let's move on to example 2. Here's A. Now they want you to find a formula for k given that A equals P times D times P inverse, and they also give you P and they also give you D. So the first thing you do is find P inverse. And now the interesting thing is, if you do an A squared, since you know what A is, A equals P times D times P inverse, if you multiply two of these things together, this inner P inverse and P cancel out to the identity matrix and disappears. What you're left with is a D squared sandwich in between a P and a P inverse, okay? Here it is again, a D squared sandwich between a P and a P inverse. So you just, and we know how to calculate D squared from example 1, so you just need to form this trio of matrices, okay? And that's how you find A squared. Same thing for A cubed. You multiply another A to A squared, and the interesting thing is you get another identity matrix cancellation right here. So what you're left with is 3 D's sandwiched in between a P and a P inverse, okay? D cubed sandwiched between P and P inverse. And they didn't show the matrices, but to find A cubed, this is what you would do. And for a general A to the k where k is greater than or equal to 1, you have this formula right here. P times D to the k times P inverse, okay? Let's move on to this definition. It's kind of important. A square matrix A is said to be diagonalizable if A is similar to a diagonal matrix. That is, if A equals P times D times P inverse for some invertible matrix P and some diagonal matrix D, okay? A and D are similar, and we talked about similarity in one of the last videos. Move on. Theorem 5. The diagonalization theorem. An m by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. In fact, A equals P times D times P inverse with D a diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A. In this case, the diagonal entries of D are eigenvalues of A that correspond respectively to the eigenvectors in P, okay? So Hold on a minute. Let me read this again. An n by n matrix is if and only if A has n linearly independent. Okay, so what is this? Now what they're saying here is that you have your matrix A, right? That is diagonalizable. That means the matrix A is similar to some particular D if and only if A is composed of n linearly independent eigenvectors. Okay. Now that you know the condition whether or not A is diagonalizable, what they're saying right here is D is a diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A. Okay, so P is n linearly independent eigenvectors of A, and D are eigenvalues of A that correspond respectively to the eigenvectors in D. Okay, I hope you get that. In other words, A is diagonalizable if and only if there are enough eigenvectors to form a basis of Rn. We call such a basis an eigenvector basis of Rn. I'm going to stop right here. Right now, I think if you want more intuition, you can look at the proof, but otherwise, I think I'm going to stop this video now. Thank you.